Yeah, good morning. So this is our second lecture of the course MEE2050 Vehicle Dynamics. We were in the first class just to have kind of a big picture of the course. Essentially, the aim of that particular lecture from my side is to motivate you all to have an initial push to get attracted towards this course and significance of this course. It is really a value-added course, as this is also an elective course that you all are aware. Doing this course would give an additional credit to you as you are going to pursue a career in automotive industry, because the vehicle dynamics is a key subject or a key aspect in a product development of a vehicle. Is what will be in one way you want to say is an outcome that you'll realize at the end of the course. So in last class, we just had this big picture, what all the content of the syllabus, and we have also seen the specific objectives and outcomes that were required to be gained at the end of the course. All that we have just browsed through, and also important dates as far as your examination is concerned. So you are aware CAT 1, CAT 2 from academic calendar itself. And your quiz 1 and quiz 2 dates are also I have mentioned yesterday, and we have seen that quiz 1 after CAT 1, quiz 2 after CAT 2. There are two quizzes, and the DA is your observation, your attentiveness in the class. So I would frequently ask you to send me your notes. So you are supposed to upload the notes in Microsoft Teams. So I expect that everyone is very attentive in the class and make your clear notes from the class. And once I ask you to submit the notes once in a week or 2 weeks, then only I'll upload the class notes on the Microsoft Teams. So till then, let me see that how you are listening to the lecture and making your own notes. So that is what is a regular activity during this semester. Once in 2 weeks also, I would ask you to upload your notes, and then I would upload what are the class notes that are there in the course page. Definitely it will be before CAT 1. The portion what I cover would be uploaded in Microsoft Teams, the PDF form of class notes. Till then, I would wait that you are listening to me, you are watching the missed videos, and then you are making your own notes. When you do that, only there is actual learning takes place. Otherwise, you would have all content stacked on your files, and then you would take Xerox and then you make an attempt to do it in examination. All. So this is my experience. So please be very attentive in this online class of mine and make your observation clearly on your notebook. So with that note, let's go ahead with today's class. I'm going to teach you today a simple harmonic motion, because a mechanical vibration is what is an important basic constitute of your vehicle dynamics course. So in today's class, we are just going to look at what is mechanical vibration and its overview, and we are going to specifically look at what is simple harmonic motion. How can we represent that physical motion into a mathematical form, and what are the various aspects of solution of that is all what is that content of today's particular class. So for that, let me share my screen. So this is what is that in the first lecture we have looked at an important flow chart that integrate driver, vehicle and ground system. And that is what does that we have used to get a big picture of our course in terms of the deliverables of a vehicle as performance, handling and ride fall into three important categories of dynamics called longitudinal dynamics, lateral dynamics and vertical dynamics respectively. And this vehicle performance are measured in terms of these dynamics aspects because of necessary inputs through driver and other external environment, your ground condition, aerodynamic input, road condition, and so on. So the one who drives the vehicle is called the driver, and he has to be very much alerted all the time visually what's happening around the vehicle, and he has to give a necessary inputs through steering as well as to his foot pedals. So this is what constitute the motion called vehicle motion in vehicle driver ground integrated system. This is what we have seen in the last class, and today's class I said we will go ahead with looking at an important aspect of mechanical vibration that falls in our first module. You are going to learn fundamentals of mechanical vibration. So this is lecture number 2, and today's date is 04/08/2021. So what is mechanical vibration? What is mechanical vibration? So if you look at mechanical vibration, can be defined as this way: is the motion of a particle or a body which oscillates about a position of equilibrium. So for example, I can consider entire vehicle mass is a point mass. So in engineering mechanics, you have studied the entire mechanics with two important ideology. What are those two ideology? One is called particle mechanics. Another one is called rigid body mechanics. So you have studied with these two ideologies the entire rigid body mechanics course called an engineering mechanics course, and that course is a prerequisite for this. So all of you have finished that course. So what is particle mechanics? Particle mechanics is not studying about motion of tiny particle, which is not a mass, which is a massless particle. It is not so. It is studying about bodies only, where its physical geometry is neglected. So entire geometry is confined to a point mass. So we consider only the mass or weight of the body, neglecting the geometry. Then the rigid body can be treated as a particle, so that it simplifies the system of forces acting on the body to be concurrent. So you will have a concurrent system of forces, right? And then the effect of this concurrent system of forces is only translational motion. So you will not have any rotation. That's the ideology of this particle mechanics. So now when you call mechanical vibration, it is again a motion. So what is the mechanics definition? It is a physical science which deals with the system of forces and its effect on bodies which are under stationary condition or in moving condition, we see. When it is under stationary condition, that falls under the category called statics. When it is under motion because of unbalanced force and not constrained bodies, that is called dynamics. So mechanical vibration falls under dynamics of rigid bodies as a special motion called an oscillatory motion about its equilibrium. So it is an oscillatory motion. It is an oscillation about a position of equilibrium. So this equilibrium is going to be a static equilibrium point or stable equilibrium point of a mechanical system. And this motion is what is otherwise also can be called as a simple harmonic motion. The motion which is executed is what is called a simple harmonic motion. So we are going to study that in today's class. So this most vibration in machines, see this vibrational phenomena can be observed where in many of the machines, especially in our course vehicle dynamics, you see the vibration is an important aspect which is going to decide the comfort level of the passenger or driver inside the vehicle. So that vibration should be accounted during its design. So what does that means? This vibration is not desirable. It is an undesirable event in case of a vehicle vibration, and we have to look for how can we minimize this vibration. So this vibration is all going to be accounted by its magnitude of vibration and its frequency of vibration, and another thing it's called its phase of vibration. So this phase angle, frequency and magnitude are called an amplitude, is what is characterizing any vibratory motion of the mechanical system. So we are going to look at them in our class. So this can be best understood by means of looking at simple motion, schematic motion of a mass attached to a spring. So let's just look at, I have here a spring. So this spring is of its free length is this, and I attach here a mass m. And then what would happen to this spring is this spring will have its deformation, elongation. So here, this is characterized by constant called spring constant or stiffness of the spring. And I attach a mass here at this end of the spring. So this is free length of the spring. And then what will happen, since you attach this, now the spring is going to get deformed and it is going to take a position called a stable equilibrium position or static equilibrium position. So this mass m is here, and now this position is what we call it as static equilibrium position or stable equilibrium position. Stable equilibrium position. So this is of its constant, spring constant. So you have this. So now the state of this mass or the particle attached to the spring is what? It is stationary, it is stable and is resting there. So now if I look at my free body diagram here, what is that I draw? I will have my free body diagram. And the free body diagram is the one isolate the mass and show the forces acting on them. So the active forces are its weight, that is the mg, and the spring would always try to go its free length. So there will be a force acting on the mass exerted by the spring called a restoring force, that is. So that force is what is now F is given by K into delta St. So what is this delta St? Delta St is what is now this displacement. So this distance it is deformed is what is static deformation or delta St, deformation in the spring. So there is no motion, so other side it's zero. So I will have here this mg is what is nothing but W. So W is down. So let me consider here my convention from here downward positive. So if I consider that, then this force down is positive, I consider. So the force up is negative, that's K into delta St. So that's going to be 0. So W is equal to K into delta St is what is equation number 1. So this is what is its static equilibrium position or stable equilibrium position. So now, how do we impart the motion into this body is what is going to define mechanical vibration, because that's going to make this mass to oscillate up and down with reference to about what? About its equilibrium position. That's what we define here as an oscillation about a position of equilibrium is what is defining mechanical vibration. So how do you do that? You would have some initial displacement and leave it, and then you will have this. So I would be now pulling this mass down some distance, and then I release it, and that is my start of motion if I consider. and the motion would be executed is what is called the simple harmonic motion or vibratory oscillatory motion, right? So let us now look at, so now this spring is further stretched from delta xt, and let me consider that distance here. So from this position, let me consider now uh, any position x given. So if I consider that, here I have my mass m, and let us consider it can be going up till this point where this is from this reference point as maximum m. So that is what is called maximum displacement or amplitude of this oscillatory motion. So now I consider here this mass from the static equilibrium position to its maximum displacement amplitude, and in between I consider, so in between I consider this goes down motion, and I draw its free body diagram. How is it going to be? I would have here in this I will have, let me draw this free body diagram here. So I will have here the weight acting down, that is W, and I'll have my spring force. So spring force would be K times its deformation from its free length, that's important. So that's going to be what? X plus delta ST. It is not spring force from its equilibrium, because already there is a spring force that is balanced by the weight, that is spring force, because of this deformation from its free length. So when you say the spring force, it is always what is the deformation of the spring from its free length. So at this state of free body diagram that we draw, you have weight acting down and the spring force acting up, and given by K multiplied by X plus delta ST. And now it is not under rest condition, it is under motion, and that is caused by force, effect force called mass times acceleration. So m times a, mass times acceleration, or this can be written as m times x double dot, because a is d squared x by dt square, v is dx by dt, where x is any position, any time t, the position of the mass that you consider. So if that is so, this is mx double dot acting down. So now if I apply Newton's law, so what is my equation in this free body diagram? So I will have W, this is what is free body diagram, this is what is called kinetic diagram, and you have W plus minus K into X plus delta ST. The other side it is mx double dot, mx double dot. So now W minus Kx plus minus K delta ST, that's equal to mx double dot. So you would have now this cancels each other because of equation 1. And what is that is remaining is on one side minus kx, on the other side it is mx double dot. So if I bring on the other side and rewrite this equation, mx double dot plus kx equals 0 is what is equation number 2. And this equation is what is called the governing equation of this oscillatory motion. So this equation 2 is the governing equation of this oscillatory motion. So you have to see now how this motion going to be executed. So now at this point you see this position at stable equilibrium, the state of the mass is resting. And then when I displaced it and released it, then it is executing motion this. So the motion from the static equilibrium till here, it comes because of two reasons. I can give some initial velocity from there, or I can pull that mass to its highest amplitude and release it. Then what will happen? It will be executing its oscillatory motion up and down. So like on one side, a positive xm that you have as this dotted line, you'd also have from here symmetrically up minus xm. So this mass here is going to oscillate between these two amplitudes. And that motion is going to be a projection of, can be imagined as projection of a particle going around a circle with a uniform velocity on its diameter. So you can consider this xm to minus xm as a diameter of a circular path on which the particle goes around with the uniform velocity. You can imagine like that. So if you look at and project it on diameter, if you see, the particle will execute motion from extreme to extreme and comes back like this. So if your motion starts from this extreme position, so it goes up there and comes back again here, is what is called one cycle of motion. So like that it will repeat indefinitely many number of motions with an important assumption that the system is conservative. There is no friction, there is no air resistance. If you make such an assumption, this initial disturbance that you give, either giving a displacement and releasing it, or giving some initial velocity and observing it, no matter, you would see that motion will ever continue with an important assumption of no resistance for its motion, no friction involved in this. There is no dissipation involved in this. Spring is going to restore the energy and use that energy again. So if that you understand, at this point of extreme position is what is that called its maximum potential energy position. So when you release it, the spring force would excite this motion. So as it gains from that point velocity, it would have a maximum velocity at its mean position. What is mean position? Is stable equilibrium position. At that position, since that gain velocity would make further its motion to this end till xm, and there you get velocity 0 and gain your potential energy maximum, and because of that energy it would be reversing back. So these two extremes are called the point of reversal, where you see velocity 0, so they will have a high potential, maximum potential energy in the system. And at the stable equilibrium, you see that x is 0, that means the potential energy is 0, but it will have its maximum kinetic energy. Other than these positions, if you see the one which is shown here, it possesses both potential and kinetic energy. The total energy of the system remains same, is what is conservative system. And having simply representing an oscillatory motion of your body as a spring and mass system, you refer that to a conservative system. But in reality, the structure do have an effect of dissipation, and that material property called damping will be introduced. We will see that in our subsequent class. And today's class, we just look at with this elementary model of this, and this is confined to go motion in one direction. So this is 1 degree of freedom vibration model, right? So what is the independent? What is the independent variable here? Is x is the independent variable. So at any point of time, what is this x is what we have to get, and that's what is called the solution of this equation. I'm going to explain you now further. Yeah, yeah. So you see that now how do you define the solution? So this oscillatory motion is called a simple harmonic motion, which is characterized by the fact that we are aware and we know the acceleration is proportional to the displacement and act opposite in direction, right? Is characterized by the fact that acceleration is proportional to the displacement and opposite in direction. So this is what is simple harmonic motion. So that's exactly what I was explaining. Also that if you look at motion of a particle that goes in a circle, So let me take a circle here. In this circle, if I consider a particle motion at any particular point, say this is here, and this particle projection on the diameter. So this is its diameter. So this particle goes with the velocity Vm, constant velocity around this. Its projection onto this, let's say this is point P, and it will go up and down. So this is xm, this is minus xm. If we consider this motion of P as this goes around would be moving up and down. Right, if you look at here, we'll have some vectors, interesting vectors, and then you'll see those vectors in our equations as well when we go and post our trial solution and solve. So what is that you are going to see here is, let me have this point as O and join this point O to this point, where this point is Q. This point is Q. And I have here, interestingly, two vectors. One is this, another one is this vector. And this vector is C1 and this vector is C2. And you see now this angle between this vector OQ and C1 is what is called phi, called the phase angle, which I was mentioning in vibratory motion. We will have to realize this all. This diagram is very interesting diagram. We will try to understand that. So you also have now a horizontal diameter in this. So now the C1 vector initially positioned from this at a distance called omega nt. This is omega nt. Let's understand what is this omega nt all as we progress. So this vector diagram is what I'm going to explain you, and you would understand the simple harmonic motion as well, the solution for the governing equation of this oscillatory motion. So how are we going to go further is in this way. We'll get back to this diagram then and there as we progress in deriving the expression of its solution. So you consider now its solution. So the equation what we had, our governing equation number 2 is mx double dot plus kx equals 0, right? So in this equation, I can substitute x1 equals sine omega t or x2 equals cos omega t. So if I substitute both of this in this equation, that satisfies. That is what we call it as a trial function. So what I will do, I will consider a solution, a position of x given by C1 x1 plus C2 x2. So C1 and C2 are some arbitrary constants multiplying with this x1 x2. I combine them, and this combination is what is my trial solution or the general solution for this is the general solution of this governing equation 2 of this motion.
So it is C1 x1 plus C2 x2, right?
Yeah, C2 x2, correct. So now here by substituting x1 and x2, what is that I'm going to get? It is going to be C1 sine, in this place it's omega. So here you can see this, I can rewrite this as x double dot plus k by m x equals 0, where this is again can be written as x double dot plus omega n squared x equals 0, where this omega n square is what is its circular frequency of oscillation. Of oscillation. So oscillation, what is that is omega n, where omega n is circular frequency of oscillation. So this omega n can be obtained by under root of k by m, which are the parameters of the body. So if that is so, I can write here as under root of k by m t plus c2 sine under root of k by mt. I would take this instead of sine cos. So when I put here, this is cos, x2 is this, so this is cos. So this is my general solution for this motion. So the question comes now, how do you get the values of C1 and C2 of this general solution? Correct. So how do you get C1 and C2 is what now we have to understand. That's exactly would be obtained from the initial condition of this motion. Right. So how are you going to do that? And see, this is the periodic motion or this function x, c1 sine of under root k by mt plus c2 cos of under root k by mt is a periodic function of time and therefore represent the vibration of a particle p represented here projected on this diameter. Right. So now let's find out the coefficients here. So how do I go about finding out the coefficients here is, let me explain. So let's consider the initial condition at time t equals 0. What is that? I can have two possibilities. What is that I was telling? You can either give an initial displacement and leave it with the zero velocity, or you give an initial velocity from zero displacement position. So that are the two conditions. So at t is equal to 0, when I say v naught equals 0, that means it is given some initial displacement. Then if I substitute that in this, what does that I'm going to get? So for that, let's do one thing beforehand. Find its derivatives as well. So I'll rewrite this equation x as c1 sine, this under root of k by m is nothing but natural frequency, circular frequency of oscillation. So omega n t plus c2 cos omega n t. So if I differentiate this, I would get velocity, right? That would be x dot. So x dot would be equal to v. That's going to be differentiation of this. That's going to be c1 omega n cos omega n t minus c2 omega n sine omega n t. Similarly, x double dot is going to be its acceleration, and that's going to be again here minus c1 omega n square sine omega n t minus c2 omega n square cos omega n t. So let's call this the equation 3, 4, and 5. Right. So now the initial conditions are at t is equal to 0, you have velocity is 0. So if I substitute that here, velocity is 0 in equation number 4, what is that I get? T0, this term goes off. So I will have this term 1. So I will have from this equation 1. A minute. So this boundary condition t is equal to 0, v naught equal to 0, I will have c1 equals 0. I'll have c1 equals 0. Right. I will have c1 equals 0. Okay, just let us take this condition t is equal to 0, v naught is equal to 0 from equation 4. I will have c1 equals v by, that's become v naught by omega n, right? V naught by omega n. Another initial condition possibility is what at t equals 0, I can have x naught equals 0, and you'll have some initial velocity. So if I substitute that in the equation 3, what I'll have when I say t equals 0, this term is going to be 0, and this is going to be c2, and this is going to be 0. So I'll get from this c2 equal to 0. I'll have c2 equal to 0, and I'll have here this is equal to this. Right. So now having these two constants putting in my equation x, I will have my general equation. And that is the general solution. So we can also represent this in a compact form. So very compact form. So let's have these constants found out. As set of equation 6 and this is 7. These are the two initial your arbitrary constant values, and your equation x is going to be now C1 is V naught omega n sine omega n t plus this is going to be if I substitute C2 0, this is not there. So this is going to be 0. So I can either have this or so I get my equation this. So here what is this is going to be my amplitude, that is my xm, that's my xm. So here C2 0 I can't substitute. So that's what you have to be very careful. You will have a compact form. So how do you define that is in this way. So there are two cases here. This case 1 to initiate your motion. This is case 2. So in case 1, when t is equal to 0, V naught equal to 0, what is that you get is C2, C1, one minute, just give me a minute. You would get these two. So see, let me write in a compact form. So that compact form is going to be, yeah.
But in case 1, do we have initial velocity or it is taken as 0? So if we take 0, then C1 will
Initial velocity 0 means what you understand is there is the displacement x, right? See, how do you give this initial velocity 0 and you start your motion is again look at here carefully. I pull this mass from its stable equilibrium and I release it. So when I release it, that velocity is 0, and then it's gain its velocity because its acceleration is directly proportional to the displacement, and that is acting towards its mean position in simple harmonic motion. So when t is equal to 0, I consider it is in a displaced position here like that, and I release it, and that will execute the motion. So you are here when you write this case 1 initial condition. To start your oscillatory motion, either I can do at time 0 velocity 0, that means I give some initial disturbance. So initial disturbance means I give x naught. So t is equal to x naught. So when sorry, not t equal to x naught, x is equal to x naught. X is equal to x naught or xm something, right? So if I give x is equal to x naught, this if I substitute in this at t is equal to 0, x is equal to x naught, what is that I get? C2 is x naught. C2 is going to be x naught. C2 is going to be x naught in this case. Similarly, if you look at case 2, at t is equal to 0, I don't give x naught, rather I give some initial velocity v naught. So what does that mean? I just to give an impulsive force from its mean position. Instead of gently pulling it and starting its motion, when it is there here, I just hammer it. With that. So I impart some impulsive force that would have its velocity, and then it will execute the motion. So what is that time? The velocity is given, and the displacement, the position x is 0 at that point of time. So this is what is happening to initiate this oscillatory motion. So that is case 2. At t is equal to 0, x naught is 0. There is a x dot would be some v naught initial velocity. Then if I substitute this in this, what is that I get? T is equal to 0. This is 0. I'll get C2 is 0 in this. And if I substitute that in this, it's V naught and t is equal to 0, I'll have C1 is equal to V naught by omega n. V naught by omega n. In this, if I substitute t is equal to 0 and x naught is equal to x is equal to this 0, I'll have c2 0. That's correct from equation 3. And initial velocity v naught is there. So if I put v naught t is equal to 0, I'll have v naught is equal to c1 omega n, and this is 0. So I'll have c1 as v naught by omega n. So I get this. Right. So you see at one place I have C1 in both the cases I have now C20, right? So the case 1, when I substitute T0, I have some initial position x naught, T0 it's C1, this 0, C2 is x naught. So C2 is x naught. So in this case C2 is x naught. So like that it comes. So what is happening? It is two individual cases to execute the motion. But once the motion is started, to get this combination, that's what we see that we don't write its solution as only by x1. It is also satisfying by its own. This satisfies this equation. This also satisfies this equation. But we combine them and write it in a most compact form. If we are doing that, then what will happen is this. So you see this now represented by these vectors. So one is C1 vector, other is C2 vector, and this C1 and C2 vector are at 90 degrees. And the resultant of these two vector is what is OQ vector, and the projection of this Q onto diameter and looking at the motion of P is what is our motion. So now X is what? X is, so I consider this is my static equilibrium position, from there X. So X is OP vector. So if I consider X is OP vector, X, the OP vector is what is X, and that is what is now given in this compact form. I can write that vector as OQ vector sine omega nt plus phi. I can write it in this form, sine omega nt plus phi. So how does this come? See, you see here OQ, and if OP is what is nothing but projection of this onto vertical. So what is this angle here? This angle here, or I have to get this opposite side to this. So I know this angle. So this angle here is omega nt plus phi. So OQ sine omega nt plus phi is what is this line parallel to this. So that gives me OP vector. So if I have now this, accounting this phase angle in this, instead of only having some amplitude or sine omega nt, if I have this phase angle that accounts both C1 and C2 vector and both combination solution, and that is what is called compact form of this solution. So compact form of the solution where x we had C1 sine omega nt plus C2 cos omega nt can be rewritten in this form because of the introduction of this phase angle or C1 C2 vector. So now I can get my x dot from this. So now this OQ is what? What is OQ vector? OQ vector, its magnitude is the radius of the circle. That circle is what is called an auxiliary circle in this case. So this circle radial length is xm. So when you have this omega nt plus phi together is 90 degrees, then this q comes and occupy this place, right? So you see that this length of this OQ is constant, and that is what is your xm in this. So I can express OQ now by its magnitude, and that's what is amplitude of this motion. So that is xm. So x I can rewrite as xm sine omega nt plus phi, and this is going to be xm omega n cos omega nt plus phi, and x double dot is going to be minus xm omega n squared sine omega nt plus phi. So let us call these equations now as 9, 10, 11, 12. So this is equation 9, 10, 11, 12. So in this now, xm is what is called an amplitude. And what is phi is called phase angle. So what is this phase angle? This angle is included by vector OQ and C1. So angle included by vector OQ and C1. And omega nt is what is now having here omega n is the circular natural frequency. This omega nt, when it reaches 2 pi angle, it completes one cycle. So when omega nt is 0, it starts its motion, and omega nt is 2 pi, it completes one rotation, this vector. So look at here, look at this circle, auxiliary circle. In this omega nt is this angle. So omega nt is 0, that's going to be having C1 vector horizontal, right? And that vector completes 2 pi, then it completes one complete cycle, one complete cycle. So you can see that how that motion can be visualized looking at this diagram. So I'm going to have now this angle.
Excuse me, sir.
Yeah.
Sir, it's
You
already
have a
been
class,
10
you can
and
proceed.
we have class.
Yeah, you can go. I told that you are late to the class morning. So you can proceed. I will not repeat this instruction again and again.
Okay, sir. Thank you, sir.
So you can have here, this motion is going to be something like this. So it comes here. So from here to this 1/4 of the cycle, then again from here half cycle, then this, then comes back again here, and then it's going here. So if I take from here, then it is still this. If I take it from here, and then it is still here. So that is one cycle, and that it continues. So from this point to this point, or from this point to this point, it completes one cycle. So if I project this is the point. So like that, the motion can be visualized. So it has got its amplitude on both sides. This is static equilibrium position, or its stable mean position. So you would have your amplitude from here xm. So this is xm, and this is minus xm. So like this, your motion goes, and this time, it is what is there here on this axis. This axis, it is your omega nt I can take, and the time here would be, since it completes 2 pi, it's going to be omega nt is equal to 2 pi, so 2 pi by omega n. So the t is equal to 2 pi by omega n is what is time period. Time period. Period of oscillation, right? So this is the general solution of the simple harmonic motion. So we will stop at this point of time, and we will continue from here in the next class. And you see here, the motion is continued without any external force acting on it. You give some disturbance initially. So the initial condition is what is making that the entire motion of your vibratory motion, mechanical vibratory motion, or simple harmonic motion here. And that's all because of the restoring force that is being there in your spring, and that is stored and that is released and so on. And such a vibration is called a free vibration. It is naturally happening after the initial disturbance. So it is called a free vibration. You can also have an external force acting on the system, can be a harmonic, another sinusoidal force, and then the vibration would continue in the same frequency of excitation of the harmonic force, and that is called forced vibration. So in both the cases in today's class, we have not considered an important element called damping property of the material. So if we include damping property, then the system is not conservative. There will be dissipation of energy and so on. Then the vibration is called damped vibration. So you can have undamped or damped vibration. Today, what you have studied is undamped vibration because damping is not considered. If we consider it, then it becomes damped vibration. So if damping present, the amplitude of vibration will slowly come down to zero. So the oscillation will not continue. It will be finite in time. So it will stop at a due course of time. And this is all something that you have to develop further in mechanical vibration. If you have understood clearly today's class, this free vibration motion, right? So I stop at this point. If you have any doubts, you can quickly ask. Otherwise, we'll end the lecture. I hope you are clear with what I have taught. Otherwise, please go back again to this lecture, right? I'll end the lecture now.